This conference will now be recorded.
Hello everyone, last day we have already started group 17, that means halogens, and what are the compounds when they react with hydrogen, they react with oxygen, that we have seen. Today we'll start how when they react with metals, then what type of compounds we get, and when they react with themselves, that means interhalogen. One halogen will react with another halogen, that is another different halogen. So interhalogens, their properties, there are some difference if we compare with the properties of the actual halogens, and then we will discuss oxoacids and their properties and related problems. So first, reaction with metals. Binary compound of metal with halogen. Binary compound means there will be presence of two elements. One element is metal, another one is halogen, and we will call them metal halides, because metal will be the positive part, halogen will be the negative part. So that is why positive part will be mentioned first. So it is metal halide. The direct reaction of metal and halogen, it can produce halide of the metal. Now direct interaction, two examples here we are seeing. One is cadmium metal, directly it is reacting with chlorine gas. Another one is gallium, which is from P block, basically from group 13, it is reacting with bromine. In the first case, we are getting CdCl2 and this is GaBr3. Now, why? That is just by adding direct reaction, you are getting the product. That means they are highly reactive, so that is why this type of reaction is possible. Now, most binary halides are ionic in nature because of the high electronegativity of the halogen. Because metal will be highly positive and halide, they will be highly negative. So that is why when there will be compounds formed between them, the nature of interaction is completely ionic interaction. So the bond nature is ionic bond. Okay, there is high electronegativity difference between metal and halogen. Ionic character of the halide decreases in this order. That means when metal is same, suppose you have taken same metal, just take the example of sodium, NaF, NaCl, NaBr, NaI. So when metal is fixed and it is monovalent, then ionic character will be maximum for the fluoride salt and minimum for the iodide. Because when it is fluoride, electronegativity difference between the metal and halogen, that will be maximum. And here is the difference, here is the tendency to form ionic bond. Here we have one picture when sodium reacts with chlorine gas, and this is highly, that is the reaction is occurs very vigorously, because sodium, it is having one extra electron. If it can lose this electron, it will achieve noble gas configuration. Similarly, if chlorine can accept one electron, it will achieve the noble gas configuration. So that is why sodium is will donate electron and chlorine will accept electron, and this reaction is highly explosive. So bright yellow light is generated and great deal of energy is also liberated, because this is exothermic in nature. However, Hg, that is mercury, and also the elements of group 13, where oxidation states are +3, teen +4, which is from group 14. Pb, lead, that is also from group 14. So for mercury, then group 13 elements, teen and lead from group 14 elements, they can form covalent binary halides. That means when the metallic character of the metal is decreasing, then electronegativity difference between the metal and the halogen, that will also be less. So lesser is the electronegativity difference, higher will be the tendency for covalent bond. So if it is sodium, obviously it is from S block metal, and S block metals are highly reactive metals if we compare with other metals. Okay, so sodium is highly reactive if we compare its metallic character with cadmium or gallium. Fine. So that is why sodium chloride, it is very ionic in nature, but cadmium chloride, GaBr, then halide of tin or lead, there will be covalent nature. Okay, it is not just that any metal you take and the compound MX, it will always be ionic in nature. No, that is not the case. It also depends on the metallic character of the metal. If the metallic character is highly, that is, if the metal is highly electropositive, then obviously the bond will be ionic. So example is NaCl. But if it is metal which is from D block or P block, then the situation is different. If a metal exhibits more than one, so suppose any particular metal, it can show +2 oxidation state, it can also show +4 oxidation state. Now +4 is higher oxidation state compared to +2. So when you are keeping the metal fixed and also the halogen is fixed, that is same metal, same halogen you have taken, but two different compounds are formed because two different oxidation state of the metals are present. So in that case, the halide which is higher oxidation state, that will be more covalent than the one which is in lower oxidation state. So take the example SnCl for SnCl2. So this pair, same metal, that is tin, same halogen, that is chlorine. So obviously in the first case here oxidation state is +4, this is +2. So SnCl4 will be more covalent compared to SnCl2. Similarly, PbCl4 will be more covalent than PbCl2. SbCl5 will be more covalent than SbCl3. And UF6 where uranium having oxidation state +6, and here it is +4. So this is also following the same trend. Okay, so remember, when same metal and halogens are given but oxidation state of the metal is different, higher oxidation state always lead to covalent nature. Okay, so in this slide, is there any doubt? So after seeing the reaction of between metal and halogen, next we'll see reaction with other halogens. So halogens, they can react with themselves also, and this type of compounds are known as interhalogen. Now general composition of different types of interhalogens, see X prime, that means 1:1 ratio. Then X prime 3, 1:3, 1:5, and 1:7. Now remember here the black halogen, that is the halogen which is written in black color, that halogen is larger in size, and the pink one, that is smaller in size. So X is always more electropositive than X prime. So for example, if we have one halogen Cl, another halogen fluorine, so here Cl will be X, fluorine will be X prime, and here it will be considered as central metal, and this is attached to fluorine. Similarly, if you have I and fluorine, then I will be X, F will be X prime, and this will be the central atom. And suppose the molecule is IF7, that means iodine is the central atom and 7 fluorine are surrounding the iodine, which is central. So for different category, that is XX, this is actually XX, here Y is mentioned, but actually it is XX prime, XS3 prime, XS5 prime, XS7. So under the first type, we have all these examples. See, CLF, BRF. And remember, when you are writing the formula, Cl should be, that is the larger size halogen, that should be written first because it will carry the positive charge. Larger halogen means what? As we are moving down, size is increasing, and size increasing, metallic property also increasing. So when there will be bond between F and Cl, obviously Cl will be carrying the partial positive charge and F will be towards the negative side. So that is why positive part is always written first. So the formula is not FCl, the formula is ClA. This is gaseous, and A means the state of matter are given for 25 degrees centigrade, 1 atmosphere. That is under normal condition. It is gaseous in nature. Then BrCl, and for these two now it is solid because now the molar mass is very high, so that is why it is solid. Next type is XY3. So under this type we have all these three types. Gaseous, this is liquid, this is solid. So see, as the total molecular mass is increasing, the physical state is changing from gaseous to liquid to solid. Okay. Next type we have CLF, BRF. IF5, gaseous, liquid, liquid, and XY7. Only one example is there, IF7. Now, if you are thinking that why not other examples are present, for example, why not ClF7 or BrF7? Now, you have to understand one thing. When it is Cl or Br, compared to iodine, here size is small. So, it is difficult for Cl or Br to accommodate 7 fluorine atoms surrounding it. But when it is iodine, there is enough space. So, that is why 7 fluorine can be accommodated. Okay. Interhalogens, how we can get? There are two strategies. One thing you can do by direct mixing of halogens. This is very simple. Another thing is by reaction of halogens with lower interhalogen compound. That means first process is you have taken two different halogens and you are simply mixing. But another way also you can do, you have taken one particular halogen and another compound that you have taken which is lower interhalogen. So there will be some exchange replacement reaction, and then you will get a new interhalogen. So from interhalogen you are making another interhalogen. These are all covalent compounds, and this has to be because both the atoms are from same group and all of them are mostly non-metallic in nature, right? Now electronegativity difference between two halogen, obviously it will not be very high. So that is why now it will lead to covalent bond formation, and they are diamagnetic in nature because in each interhalogen you have 7 valence electron. So it is odd number. Now when two of them will be combining together, it will be diamagnetic. Unpaired electron will not be present. Physical properties are intermediate between those of constituent halogens, except Mp and Bp. Now it means that if the interhalogen, suppose it is Cl and N, so constituent elements are chlorine and fluorine. So the physical properties of ClF, it will be the physical properties of, that is the intermediate properties compared to Cl and N. So chlorine has some particular physical properties, fluorine has some particular physical properties, but when you will make ClF, it will have properties which is in between the properties of Cl and N. But if it is a melting point and boiling point, they will be little higher compared to the original constituent halogen. Now, if we compare reactivity compared to the actual halogens, they will be more reactive, except fluorine, because fluorine itself, it is very highly reactive. So remember, when it is, suppose you have compound BrF3. So individual halogens are bromine, another halogen is fluorine. So compared to individual halogens, now it will be more reactive. But when fluorine is present, that is in this particular example, fluorine is present. So except fluorine in all other examples. So better you take another example. Suppose if you take the example of BrCl. So constituent halogens are bromine and chlorine. So BrCl will be more reactive than original bromine and chlorine as element. Okay, that is mentioned here. This is because X prime bond in interhalogen are weaker compared to same atom bond in actual halogen, that is XX bond. That is the reason. They are prone to hydrolysis. That means interhalogens, they will, when react with water, there will be some product formation and it will ionize to give rise to polyatomic ions. So that we'll also see that when interhalogens are reacting with water, what type of products we are getting. And as there are different types of interhalogen, so here 4 different types are mentioned, 1:1, 1:3, etc. So all these different types of interhalogen, depending on what type you have actually taken, depending on that, hydrolysis product will also be different. Now, if we compare their chemical reactions, now chemical reactions of interhalogens, they are having similarity with the chemical reactions that we observe for normal halogens. Okay. So next we will see that for interhalogen, what is their structure and hybridization, because there is different types of structure and hybridization when you are changing the type of the interhalogene. See, here in this table, we have all these 4 types, 1, 2, 3, and 4. So when it is the first type, that is 1:1, the corresponding hybridization is sp3. And when it is sp3 hybridization, geometry will be tetrahedral. But see, here one halogen attached with another halogen. But if it is tetrahedral, we know it is 4 coordinated. But if there is only one X prime, rest of the 3 coordinating position, what will be there? There will be actually lone pair. That means surrounding X, there will be one X prime and 3 lone pair. So that is why ultimately the shape means when you are not considering the lone pair. So omitting the lone pair, if you are considering the structure, now it is simply linear. And it has to be linear because it is simply X attached with X. Okay. So there is one bond pair, but lone pair 3. That means there will be 3 lone pair. And that structure you can see here. So this is, sorry, it is not, it is X3. We'll come to that later. Now just look at the table now. Then next is X prime 3. That is now one halogen, central halogen, it is attached with 3 X prime. Hybridization is sp3d. And when it is sp3d, that means total coordination will be 1s, 3p, 1d. So it is 5 coordination. So trigonal bipyramidal. But see, as 5 coordination, but only 3 X prime. That means rest of the 2 positions there will be lone pair. So bond pair electron, it is 3, and lone pair 2. And without lone pair, ultimately the shape will be T shape, which you can see in this case. So this is X prime 3. This is X. This is X prime. And when it is 1:5 ratio, it is sp3d. That means 6 coordination. So it will be octahedral geometry. But remember, there are only 5 X prime. That means 5 bond pair. So the number 6 position, there will be 1 lone. And the last type, which is 1:7, sp3d, sp3d3, pentagonal bipyramid. But now, all the 7 coordination side, there are 7 X prime. So you do not have any lone pair. So that is the reason here no question of omitting the lone pair arises. So geometry and shape both are same. And if you are thinking that depending on the type, how we are getting this type of hybridization, that is actually based on VSEPR. So according to VSEPR, we follow this rule, that is N equal to half total number of valence electron plus monovalent atoms attached plus minus charge. So depending on this N value for central halogen, not just central halogen, for any other compound, hybridization will be fixed. So suppose if N value is 2, that means only 2 coordination sites are there. Okay, it starts from 4. When N value is 4, it will be sp3 hybridization. Okay, so see how we will do this calculation. Here central atom is X. Now we know number of valence electron from any halogen is 7. So it will be half 7. Number of monovalent atoms attached, capital F. How many atoms attached? Only 1. It is 7 plus 1 plus minus C. What it means? Plus C means when there is negative charge present. Here negative charge is not present, so we will not consider it. And minus C is when positive charge is present. But our molecule is neutral, so this part we don't have to consider. You are getting here the value 4. 7 plus 1 8. 8 by 2 4. So that is why it is sp3. Similarly, when N equal to 5, it will be sp3d, and in this way it will go on. When it is 6, it is sp3d2. When it is 7, it is sp3d3. So this rule you will find in chemical bonding chapter, which is related to VSEPR. So based on this, we get all these hybridization. Now one by one we will see the structures. The structure found for different interhalogens conform to what would be expected based on BSEPR model that we have just discussed. So here we have taken this type X prime 3. The shape is T-shaped because if you just forget about the lone pair, what is the remaining shape? It is like T. So that is why it is T-shaped. And there are two lone pairs. So when you consider the two lone pairs, the actual structure will be triagonal bipyramidal. But without the lone pair, the structure will be simply T-shaped. Okay. So when you are getting question that is any molecule is given and it is asking for geometry or shape, you have to be careful whether it is asking for geometry or whether it is asking for shape. Sometimes you will also see that the word shape that is also mentioned by geometry. Okay. So there is a little confusion may be there, but when options will be there, you will be easily getting the idea that what is the meaning of the question. Okay. So T-shaped with two lone pair, but actual geometry is TBP, triagonal bipyramidal. Next type X prime 5. Now total how many X prime are attached? 5. But it is from hybridization we have seen it is sp3 to D2. That means total coordination site 6. So there must be presence of one lone pair. So without lone pair the shape will be square pyramid. See, this is the structure. Here this is X and all these are X prime. Now if you also consider lone pair as one of the coordination site, then overall the shape is octahedral. But if you are not considering the lone pair, remaining structure is square pyramid. Then that is only this part if you focus, just you are not considering the lone pair, then it will be square pyramid. Only one unpaired electron in an axial position of the octahedral. That is the lone pair that will be in the axial position. So in octahedral structure, lone pair always remains in axial position, not equidistant. And the last type, see, this is the structure, pentagonal bipyramidal. So this is the central halogen and all these are X prime. Now if we attach all this, it is pentagonal as if it is a 5-membered ring. But when you will attach all this, it will be called pentagonal bipyramid because this is pentagonal, there is one pyramid, there is another pyramid, upper and lower portion. So that is why the name is PBP in short. And remember here we do not have any lone pair. Okay, on the coordination side there is X prime. Now actual examples are also given. See, this is also TBP. This is also TBP. But if you are having some problem in visualizing this, it is just written in different orientation. That's it. That is, if you rotate the molecule in this way, you will get this structure. Okay. And without lone pair, remaining shape is T shape. This is IF3. This is IF5. IF7. Okay. So this is octahedral, but if you are not considering lone pair, it will be simply square pyramid. But the last one is pentagonal bipyramid. So in this table, in this slide, is there any doubt? Should I repeat any part? Hydrolysis of interhalogens. That means when interhalogens are reacting with water molecules, different products are there depending on what type of interhalogen you have started with. So different interhalogen, there will be different products. Hydrolysis of interhalogens compound give hydrogen halide and oxyacid. That means whatever is the type you have taken, 1:1, 1:3, 1:5, 1:7, one particular type will always be formed. And what is that? It is HX. So see, you will always get HX. And HX, the halogen, that is the lower halogen. Because in this particular example, the blue X, that is the larger one, and the orange color X, that is actually the lower halogen. So the acid that you will get, this acid is known as hydrogen halide acid. General term is hydrogen halide. Hydrogen halide will contain that halogen which is smaller in size, that is the orange colored halogen. But another product, so this is product number 1, this is product number 2. The second product is actually the oxyacid. Now oxyacid means central atom if E, there must be OH attached, and sometimes there is also presence of double bond O. But this part is mandatory. Okay. Now depending on what type of halogen you have taken, you are getting different types of the second product. That is different types of oxyacid. So when you have taken 1:1 type, you are getting the type HOX, where this halogen, it is actually the larger halogen, that is the blue one, and it will be called hypohalous acid. This is the general term. Suppose if X is Cl, it will be hypochlorous. If X is Br, it is hypobromous. So in this way the name will change. Then if you have taken 1:3 type, the corresponding oxyacid will be HXO2. Here it is written as HOXO. Why it is written so? Because it is signifying the OH group. But in general, if you are writing the formula, you can also write HXO2. So first you have HOX, then HXO2, then HXO3, and HXO4. So these are the 4 types, and different general term we are using. First hypohalous, halous acid, halic acid, and parhalic acid. The product derived from larger halogen, that is the blue halogen, that will have the general formula of oxyacid like this. So this formula is actually, sorry, it is there will be no X prime. X prime is for the orange one. Okay? So suppose the center halogen is X, and this formula is signifying there will be presence of double bonded oxygen, and another side there is OH also. Now double bonded oxygen, number of oxygen may vary 0 to 3. So when this oxygen is 0, that means the formula will be HOX when oxygen 0. Formula will be HOX double bond O when it is only 1. Formula will be HOX 2 double bond O when it is 2. That is XO unit, X double bond O unit 2. 2 units are there. And when it is 3, the formula will be, okay. So this is HX4, this is HXO3, this is HXO2. Okay. So the oxyacid formula you can write in general HO attached to blue halogen, and that halogen also attached to another oxygen by double bond, but this oxygen it may vary from 0, 1, 2, and 3. So depending on how many double bonded oxygens are there, you are getting different types of second product. So these are the names, and also it is given here: hypohalous acid, halous acid, halic acid, parhalic acid. So in this part, is there any doubt? The next table, here we have all the anions of oxyacid. That means if you remove hydrogen from this oxyacid, what you will get? Suppose you are removing hydrogen from the hypohalous acid. The anion that you will get is like this. Then from the second type, HXO2, the anion that you will get is XO2 minus, then XO3 minus, and XO4 minus. So these are the anions that you will get when you are removing the hydrogen. So these are the atoms. Now these are the names of the acid, hypohalous acid. But when it is anion, the name is now different. See, when you are removing hydrogen from hypohalous acid, XO minus will be called as hypohalite, and here oxidation state of halogen is +1. We have particular example, OX minus, suppose X is Cl, so it will be OCl, and the name will be hypochlorite. Similarly, for XO2 minus, here oxidation state of halogen is +3, and it is now called halite. So when it is chlorine, it will be chloride. If it is bromine, it is bromide. Okay, not bromide, it is bromide, Te. For the next type, XO3 minus, now it is halate, oxidation state +5. This is the here negative charges are not mentioned, but negative charge will be there. And chlorate is the example. And the last one, perhalate, at oxidation state is +7. It is +7. General formula XO4 minus, and if you take actual example, it is ClO4, so the name will be perchlorate. So see, ClO3 minus is chlorate, but it is perchlorate. Okay, though there is no per-oxygen linkage, but still the name is perchlorate. So is there any doubt in the formulas of the anions of the acid and also the formulas of the acid itself? Any part? Should I repeat once more? So now we will focus on this oxyacid or oxoacid. In this table you can see these are the common name, that is hypohalous acid, halous acid, halic acid, perhalic acid. Then we have oxidation state. These are the oxidation state of the halogen. Now when it is fluorine, it can have only one type of oxoacid, and the type is HOS. Okay, other variations are not present. Cl, it can have the maximum number of oxoacids. So see, all the 4 types are present. When it is bromine, you have only 3 types, and when it is iodine, then also you have only 3 types. These 2 are not present. Okay. So these oxoacids, they are stable only in aqueous solution. If you are that is separating them from water, then they will be only in salt form. Now salt form means, just take this particular example. Suppose you have HClO2. Now HClO2, it can exist only in water. But when you are removing the water, now it will be in salt form. That means it will carry charge. So this negative charge, there will be some metal. Suppose any metal MClO2. So that is, it is mentioned, it will be in salt form, which another way of saying it will be in anionic form. We cannot isolate them in pure state. That is, if it is aqueous solution, then only it can remain in these formulas, not when water is not present. Fluorine is the most small in size, and electronegativity is also very high. So that is the reason it forms only one type. Okay, remember, fluorine has some anomalous properties if we compare the properties of the other with the other members. So as it is very small in size, electronegativity is very high. So this type is only possible, because if you look at the other possibilities, oxidation state is very high, +3, +5, +7. But these type of oxidation states are not possible for fluorine. So that is the reason here it can form only one type of oxoacid. Chlorine can form all the types, and bromine will form these 3 types. And just like bromine, iodine is also forming 3 types. Okay. Any doubt? Now we will focus on the structures of oxoacid. Previously we have seen the structures of all the interhalogens. Now we will see the structure of oxoacid. In all these oxoacid, central halogen atom sp3 hybridized. and there will be one X OH bond. That means if X is the central halogen, OH bond must be present. This is mandatory because this is the structure of any oxoacid. Remember, we have also seen oxoacids of sulfur, phosphorus in group 15 and 16, right? So just like that, the formula of oxoacid, this fragment must be present. It is essentially present in every oxoacid, and sometimes there may be also X double bond O. So in most of these oxoacid, you will also find X double bond O. Only in the first type there is no X double bond O. Okay. So first we will focus on the first type, hypohalous acid, that is HOX, the simplest that is possible. Now when it is HOX, you can have all the different 4 types, that is for fluorine, chlorine, bromine. Here oxidation state of halogen is +1, and when this acid, that is this acid, there is a tendency that it will be converted to these two. That means hypohalous acid, it has a tendency to make halic acid. Remember, HOX3, this is the next type. It is having general term halic acid. So here oxidation state is +1, but in halic acid oxidation state is +3. Okay, so as it is +3, so from +1, 3 HOX, it is converted to +3, and also HX is formed. That means it is, you can say it is a disproportionation type. From +1 it is oxidized to +3 and also reduced to -3. So in this form, particular form, it is not very stable. So there is a tendency to change its form from HOX to HOX2 and HX. And how to find this oxidation state? It is very easy. Overall charge is -1. Just take halic acid, it's the corresponding ion. So halogen, if it is having oxidation state, suppose A, for 3 oxygen it is 3 into -2, -6. Overall charge -1. Sorry, it will be 5, not 3. It's +5, because if you look at this table, for HXO2 it is +3, but when it is HXO, it is +5. XO3 minus, suppose oxidation state is A, so it will be A plus 6 negative charge from oxygen, overall charge is -1, so A will be 6 minus 1, that means +5. So in this way you can find oxidation state of X here and also in the last one. So from +1 it has a tendency to convert to +5 and minus, sorry, it is -1. F has only one oxoacid that we have already seen, that is only the first type. Because of absence of d orbitals, higher oxidation state for fluorine is not possible, and that is why the other types are also not possible. Now in this particular formula HOX, if we are removing the hydrogen, it will be XO minus and the ion will be called hypohalite ion. These are the actual anion. This is general formula. And here X is central halogen, this is O minus, and all these are lone pair. Okay, so for you can see here we have 4 coordination, right, for central halogen. Now 4 coordination, one coordination side there is 1 oxygen, so rest of the 3 part there must be presence of lone pair, and you can use the same formula that we have already seen in case of the structure of interhalogen. That means you can use the formula half M plus, sorry, V plus M plus minus C. So for halogen, which is the central atom, valence electron 7, monovalent atoms attached. It is actually that is oxygen, which is not, it is monovalent. Okay, and what is the negative charge? Here negative charge is present, which is -1. Okay, so we have to consider +1, that is plus minus charge, you have to add +1 one charge because it is carrying one negative charge. Okay, but see, monovalent atoms attached, we say that is M is the number of monovalent atoms attached, and here we have XO single bond. So here oxygen is having single bond, so that is why we, as if at a first glance it seems that we should consider, but normally what happens, there is double bond between oxygen and halogen, so that is why this oxygen will not be considered. So ultimately what value of N we are getting, it is 8/2, that means 4, so it will have sp3 hybridization. So in this case the central halogen is always sp3 hybridized, but lone pair will be different, number of lone pairs will be different. So this is the first example of hypohalite. If you consider the geometry, it is tetrahedral, but because it is sp3 hybridized. But if you are omitting the lone pairs, now the shape is linear. Just focus on this part. So shape will be linear without lone pair, because there are total 3 lone pairs of electrons on the central halogen atom. Okay. Any doubt? Next one is Hall's acid. That means HXO2. Here oxidation state of halogen is +3, and the anion, corresponding anion will be XO2 minus. And actual example here we have OXO, that is, you can also write it in this way, ClO2 minus. And the actual acid is HClO2. Now this is also sp3 hybridized, right? But here 2 lone pairs are present, because the second coordination side there is also oxygen. So if you are not considering the lone pair, the shape will be like inverted V. Okay, so though actual geometry is tetrahedral, but without lone pair, the geometry will be V shape. Chloride ion has a V shape owing to the presence of 2 lone pairs on the central chlorine atom. So 2 lone pairs are fine. Third type, HXO3, but without hydrogen, it is XO3 minus. That means it is halate ion, XO3 minus. Examples are ClO3 minus, BrO3 minus, IO3 minus. Now the third position, there is another oxygen. So that is why gradually the number of lone pairs are reducing. Here we have only 1 lone pair, and this is sp3 hybridized, so geometry is always tetrahedral, but without the lone pair, see, this is simply pyramidal in shape. These are the corresponding examples. Oxidation state +5. It is pyramidal in shape, but actual geometry tetrahedral. Only 1 lone pair. Okay. And the last type, now the fourth position also there is oxygen, and the formula is HOX4, corresponding anion OX4 minus, or you can write it is better we write XO4 minus, because negative part should always be in the second position. So this is perhalic acid, but if you consider the ion, it will be called as perhalate ion. Fine. The oxidation state of the halogen is now maximum +7, and here both geometry as well as shape both are tetrahedral, because you do not have any lone pair, so no question of omitting the lone pair. Fine. So now we'll see this problem. What is the bond angle of hypochlorous acid? Hypochlorous, that means it is the first type. Remember, hypochlorous acid. Just look at this table. HOX, the first type, it is hypohalous acid, but when it is chlorine, it will be called hypochlorous acid. So the formula is HOCl. Now HOCl, it is asking bond angle. Now to find out bond angle, we have to know the hybridization. And how to know the hybridization? Just follow the formula. It is 7. Charge is 0. Number of 1 monovalent atoms. This unit is attached by single bond. So this is 4. That means it is tetrahedral geometry. And if it is tetrahedral, then what should be the angle? The standard angle, we know it is 109 degree, 9.5 degree. Okay, so that is why it will be the correct. It is sp3 hybridization. Any doubt? Should I repeat any part? Is the question clear? So next you will see their acidic properties. That means as they are acid, we are saying it oxoacid. So there must be some, so it is 109 degree. Actually, if we see the value, it is 109.28 minutes. Okay, so the nearest value will be this one, not 0.5. In any series of oxoacid of halogens, the first member possesses high acidic strength. Okay, so high acidic strength means in any series of oxoacid, first member possesses high acidic strength. This is because of high electronegativity and small size of the respective halogen. Now, when we are talking about series, basically for any particular formula, so there are different formula of oxoacid. But suppose you have fixed the formula. Suppose you have taken the first type HOX. Then the first member, that means when X is F, all the types are HOF, HOCl, HOBr, HOI. So the first member will possess high acidic strength. That means if you are given some examples, see, suppose you have been given these 4, all are having same formula, that is HXO4, but you are changing the halogen. So here when you are changing the halogen which is having maximum electronegativity, that will be most acidic. So this is the acidity order. In any series of auxiliary halogen, first member will possess high acidic strength. Similarly, if you have taken another formula HOX, you are just changing the halogen IBrCl. Now electronegativity of chlorine is 3, bromine 2.8, this is 2.5. So electronegativity of Y is increasing in this direction. Acidic strength will also increase in the same direction. Reason is high electronegativity and small size of the respective halogen. But if you are keeping the halogen fixed, but you are changing the formula, that means here halogen is chlorine, but you are moving from HOX type to HXO2 type, HXO3 type, HXO4 type. So now you are changing the formula. So halogen is fixed. How the acidic strength will change? As you are moving from HOX to HXO2, HXO3, HXO4, it will increase. And why it is so? Because oxidation state is increased from +1, +3, +5, +7. Increase in oxidation number of the halogen. And here we also have another explanation, that is as oxidation state is increasing, so that is acidic strength is increasing. That is one explanation. Another explanation is also there. Without the hydrogen, this is the conjugate base, that is for any acid HA, the conjugate base is A minus. Now conjugate base of HOCl, it will be ClO minus. Conjugate base of HClO2, it will be ClO2 minus. Now for the first conjugate base, you have only one structure. For the second conjugate base, you can have two resonance structure, number 1, number 2. How you are getting? The negative charge is making double bond, and here we have negative charge. So these two structures are equivalent. Fine. Similarly, when it is HClO3 corresponding anion ClO3 minus, you are having 3 resonance structures. And all these 3 are equivalent. Here also you are having total 4 resonance structures. All the 4 are equivalent. So I mean to say, as we are moving from the anion ClO minus to ClO2 minus, ClO3 minus, ClO4 minus, number of equivalent resonance structures are increasing. And higher is the number of resonance structure, higher is the stability of the conjugate base. Okay. So as number of resonance structures are increasing, so that is why conjugate base A minus, that is having more stability. So when conjugate base is highly stable, the corresponding acid is also very, very acidic. So suppose HA is any acid, not just oxoacid. Suppose you can also take the example of, in general, any acid. So it is dissociated as H plus, A minus. Now when we say HA is very acidic, when number of H plus is very high, that means when dissociation is very high. Dissociation of what? Dissociation of HA to H plus and A minus. Now if A minus is highly stable, that means equilibrium will be shifted from left hand side to right hand side very easily. So when A minus stability is very high, the acidity of HA is also very high. So here conjugate base is stable because of increasing number of resonance structure. So that is the reason, as we are moving from HOCl to HClO2, HClO3, HClO4, acidity is increasing. So one explanation you can give on the basis of increasing oxidation state. Another explanation you can give, number of resonance structures are increasing for the conjugate base. Fine. So this is maximum acidity. This is the acidity order. So here, any doubt? Should I repeat any part? Here we have problem. Different formulas for interhalogens are given in column 1 and in column 2. Total 5 different shapes are given. 1, 2, 3, 4, 5. But here we have only 4. So 1 will be extra. But that is not a problem. So X prime, that is the first one. If we want to know the shape, what we have to do? We have to apply this formula. Number of valence electron for X, it is 7. Number of monovalent atoms attached 1. No charge, so it is 4. Similarly, for the second, so it will be sp3. But only one X prime. So rest of the 3 position there will be lone pair. Okay. So it will be like this, X prime, and there are 3 lone pair. So this is actually linear in nature without lone pair, that you can understand from this. So A will be related to 3. Now if A is related to 3, you can easily cancel out these 2 options, because only in option 1 and 4 A is related to 3. So you have to, now you are stuck between these 2. Now for the next one, the calculation will be half 7 plus 3, because 3x prime plus minus 0, because there is no charge. Now it is 5, that means sp3d, trigonal bipyramidal. But there is only 3x prime, rest of the 2 position there will be lone pair. One X prime here, another X prime here. So without lone pair, the remaining shape is like T. So this is T shape, that means B is related to 1. Now when B is related to 1, you can easily cancel out option 4. So just by solving 2 structures, you can easily understand correct option is 1. So you don't have to do all the other 2. So C, that is XX prime, it will be related to square pyramid, and XX prime 7, that will be pentagonal bipyramid. Fine, that is sp3d3. And this is octahedral geometry, but one lone pair, so that is why Shape is square pyramid. Hybridization of ICl7. So this is which type? This is type X, X prime 7. Now central atom X is I. X is I, X prime is F. Okay, you have to find hybridization. That means you have to use this formula, or another way also you can do. For iodine, ground state electronic configuration 5s2 5p5. But when it is excited state, these two pair will be broken. Also this one. So now you have total 7 unpaired electrons. So all these unpaired electrons, they will form bond with 7 chlorine. Okay. That means here the hybridization will be sp3d3. That means it is actually pentagonal bipyramidal. So sp3d3 means this will be the correct option. Okay. Any doubt? You have already also seen it here. That is sp3d3 in the previous. Uses of interhalogens. These are utilized as non-watery solvent. So suppose you need any solvent which must be non-aqueous, so it can be used as solvent. Obviously those interhalogens that are liquid. They can be utilized as catalyst in some reactions. UF6, which is used in the enrichment of 235 uranium, is produced by using these two interhalogens. So you have taken uranium, you are treating it with ClF3, and you are getting UF6. So this is used for the synthesis of UF6. These are also utilized as fluorinating a compound. That means it can supply fluorine atoms. Also this example you can use for this last statement, that is U is fluorinated by the use of ClF3. Here we have a question. Greenish yellow gas reacts with an alkali metal hydroxide. That means having formula MOH metal hydroxide, alkali metal. That means group 1. It forms halate, and this halate can be used in fireworks and safety matches. So what is this gas? Now here, this information is enough to choose the correct option, because greenish yellow gas, this is possible only for chlorine, not for iodine or bromine. So these options will not be correct. This is for this one. So even if you do not know what is the halate, that is which halate is used in fireworks or safety matches, then also you can choose the correct option. So this is the actual equation. Chlorine reacting with alkali metal hydroxide, it is producing halate, that is chlorate, ClO3 minus, and chlorine is greenish yellow gas that we already know. It is used in fireworks, safety matches as oxidizing agents. Option 2 is the correct option. The last question in today's class, correct order of acidic strength we have to find. Now here in the first option only you can see this is oxide of halogen, then oxide of group 16 element, then group 15. So here oxygen is common, but groups are changing 17, 16, 15, that is phosphorus, sulfur, chlorine. And oxidation states are also different. So with respect to oxidation state, you cannot give the explanation. But as we are moving from group 15 to 16 to 17, non-metallic character increases. Now non-metallic character increases means what? It will be non-metallic oxide. They are acidic in nature, and non-metallic character maximum in 17, then 16, then 15. So this order is actually correct. Any doubt? So that is why this will be the correct option. And if you look at the other options, here also carbon is from group 14, nitrogen 15 group, this is 16. That means SO3 should be maximum acidic, but the order given is not correct. Similarly, here we have different metals. Sodium from group 1, this is group 2, this is group 30. That means this should be maximum acidic, but here order is given reverse. And the last one, this is group 1, this is group 2, this is also group 2. So this will be maximum basic, not maximum acidic. So correct option is option A. Is there any doubt in all the slides of today's class? So we are ending the session here. Thank you for listening.